Previously, I made a video about how Pac-Man uses random number generation in its gameplay mechanics. The only time it comes up is when a frightened ghost runs into an intersection in the maze. It uses a random number to choose which direction to go. Many people were curious about Miss Pac-Man too. Being such a straightforward modification of the original, did Miss Pac-Man utilize RNG for additional reasons? And if so, did it use the same somewhat flawed method of generating numbers? The answer is, yes, it did come up with some more uses for randomness in its gameplay, and it even uses a better RNG function than the original Pac-Man. This video will go in-depth about all the ways Miss Pac-Man uses random number generation, so let's get into it. Retro Game Mechanics Explained is brought to you by its YouTube members, Patreon supporters, and viewers like you. Thank you. Miss Pac-Man uses random number generation in 4 distinct ways. The first of which is just the exact same reason as the original Pac-Man, for the frightened ghost movement at maze intersections. In fact, the algorithm for this case was untouched. Only for this mechanic is the original method for generating randomness used. If you watched the previous video, you'd recall that the output of this algorithm was dependent on the first hex 2000 bytes of the game's ROM data. Out of these 8,192 bytes, 69 of them are different in Miss Pac-Man due to small patches to the code that had to be made to tie in the new content, which is just under 1%. This is enough to change the odds of the ghosts picking a certain direction by 1/10 of a percentage point. So essentially, nothing changed here. That's all I'm going to talk about for this particular use case, so if you'd like to know more about how frightened ghosts move, please do watch the previous video. It also explains why the frightened ghosts tend to prefer to turn left at maze intersections. The second way Miss Pac-Man uses RNG is for determining which direction non-frightened ghosts turn at intersections. I suppose it was understood that the ghosts were way too easy to manipulate and predict their movement in the original Pac-Man, so Miss Pac-Man solved that issue by tossing in some random movement to the ghosts, even when they're not frightened. Now, if you watched the video I made on the Pac-Man Ghosts AI, you'll understand the concept of a ghost's target tile. Whenever a ghost is not frightened, it is assigned a single tile on the board to try to move towards. Every time it hits an intersection in the maze, it will choose the direction that minimizes its distance to the target tile, regardless of any paths in the maze. For example, if a ghost were approaching this intersection, it would have to choose between going up and going left. Say this was its target tile. Even though it's pretty obvious that the ghost should turn up if it wants to reach this tile, it will choose to go left here because going left reduces the distance to the target from this particular spot. All 4 ghosts' target tiles update every frame during gameplay, and this is how they chase Pac-Man and Miss Pac-Man around the mazes. That video also explained the concept of the scatter and chase phases. The ghosts don't always chase Pac-Man. There are certain periods of time where the ghosts will scatter away instead. This is done by setting their target tiles to each of the 4 corners of the maze. In Miss Pac-Man, the phases are a bit different. First of all, there is only one scatter phase, and it's at the very start of each level. It doesn't really last for long, only a few seconds, then chase mode persists for the entire rest of the level. The main difference here is that Blinky and Pinky specifically have randomized target tiles during scatter mode. Inky and Sue still go into their respective corners, if they even leave the ghost house before scatter mode is up. You can notice this on the later levels since all of the ghosts leave the house immediately, and they move a lot quicker. This little bit of randomness at the start of each level pretty much guarantees that there won't be a sort of setup you can perform by moving Miss Pac-Man in a predetermined pattern. How does the game do it? Well, let's take a look at the code. First, we'll take a look at Pac-Man's code. Each of the 4 ghosts act nearly identically, but they each have their own routine in the code. The point of interest here is this find shortest direction function call. It expects 3 arguments: the ghost's current position coordinates in the HL register, the ghost's current facing direction in the A register, and the ghost's target tile coordinates in the DE register. The 3 instructions before this call load in those 3 arguments for each ghost respectively. After the function returns, it spits out the direction the ghost should face. The HL register holds the direction in unit vector format, with the x and y coordinates separated into 2 bytes, while the A register holds the ID of the direction. And that's all for the scatter mode code per ghost. Each of the 4 ghosts has a different target tile, which corresponds to a different corner of the maze. Now, what changes in Miss Pac-Man? In Blinky and Pinky's case, the LD instruction that originally set up the target tile has been replaced by another function call, a routine that gets a random target tile. This function just supplies the DE register with a randomly generated target tile coordinate pair, which we'll look into more depth in a moment. For Inky and Sue, however, a different LD instruction is replaced with a similar function call instruction. I would have to go on a massive tangent about how and why this might be different, which I don't have time for in this video. I'll have to make a follow-up video about this because it would also touch on how exactly a Pac-Man arcade cabinet was upgraded into a Miss Pac-Man cabinet back in the day. Let me know if you're interested in that in the comments. However, the important part here is that for these 2 ghosts, even though this function call exists here, the following LD instruction immediately overwrites the DE register with the old target tile coordinates from the original Pac-Man, which is why Inky and Sue wouldn't move randomly at the start of the level if they happened to leave the ghost house before scatter mode concluded. Now let's take a look at this get random quadrant routine. This seems like a lot, but hey, this is assembly code. What did you expect? It's actually pretty simple. First off, here is the full get random quadrant routine. These 2 entry points here are the weird bits from Inky and Sue, since those call instructions before took place of the LD instruction that prepared the A register. That has to be done inside the routine here. Over here we have 4 tables that consists of 4 coordinates. One set of coordinates corresponds to each of the 4 different mazes. This entire function will ultimately randomly select one of the 4 coordinates in this list, based on the current maze. This means that each of the 4 mazes has 4 different coordinates that can be selected for the random ghost movement. For the first maze, the 4 coordinates just happen to coincide with the 4 target tiles for the 4 ghosts' scatter mode targets from Pac-Man. The second maze's coordinates are identical to the first. The third maze's coordinates are almost identical, but they are rearranged for some reason. Also, due to what I presume is a typo, the bottom left target is not in the far corner, but rather in the middle bottom of the maze. And the fourth mazes are identical to the first 2, just in another different order. Maybe at some point these were drastically different per maze, but really they ended up being essentially identical. First, this routine selects one of these lists of coordinates based on the current level and which maze is currently in play. It does this by indexing into this list of pointers to lists. It uses this subroutine to convert the level number into a maze ID, since it's not trivial to map one onto the other. I'll let you take a quick look at this if you'd like, but it's not super important to understand exactly how that happens here. Then it generates a random number and logically ANDs it with 6, which ultimately results in choosing between the numbers 0, 2, 4, or 6. Then it uses this as an index into that list of coordinates to pick which coordinate pair to supply as the target tile for this ghost. The indices being multiples of 2, since each pair of coordinates is 2 bytes long, 1 byte for the x and 1 byte for the y position. But what is this R register? How is there just a random number register available? Well, it's not exactly a random number register, but it gets the job done here. The R register in the Z80 architecture is the memory refresh register. Without getting into too much of the details of how the Z80 hardware works, this register's entire purpose is to be sent on the address lines in order to refresh dynamic RAM while the CPU is busy decoding instructions, so that the contents of the RAM doesn't decay away over time. This register is automatically incremented by 1 for every single instruction executed, wrapping around at 127 back to 0, since it's a 7-bit counter. The highest bit is still accessible and usable by the program. This means that the exact value in this register isn't particularly well known. It depends on exactly how many instructions have been executed since the last time it was read. Because of this, it's an easy and cheap source of pseudo-random numbers, and works well for situations like this, where it isn't absolutely necessary that the outcome is purely random. As we'll see later in the video, this register is how Miss Pac-Man sources all of its RNG, apart from the frightened ghost movement that just fell back on the original Pac-Man's implementation. You might be wondering why Pac-Man didn't use the R register for its random number generation. While I can't know for certain, it's probably just due to different developers' programming styles. Pac-Man was programmed in-house at Namco, while Miss Pac-Man was coded by those part of General Computer Corporation. Since the R register wasn't really designed to be used in this manner, maybe it just wasn't known to be an available option to use in the first place. This is possibly an example of developers learning how to better utilize hardware the longer it has been available. Okay, back to the other uses for the RNG. Both of the remaining random elements in Miss Pac-Man have to do with the fruit. Just like in the original Pac-Man, there are 2 fruit to be collected in each level. The first level has cherries, second level has strawberries, then oranges, pretzels, my favorite fruit, then apples, pears, and then level 7 has bananas. Starting on level 8 though, the fruit picked is completely random. Here's the code that chooses what fruit to use. First, the level number is loaded into the A register. If it's less than 7, then that is used as the fruit index directly. Otherwise, a random number is loaded into A using the R register again. This time, the value is logically ANDed with the constant hex 1f, which will give a number between 0 and 31. Then the remainder of this value, after being divided by 7, is calculated using this loop, which subtracts 7 over and over again until the result is negative. Then by adding 7 back once at the end, it finds a number between 0 and 6. This is used as the fruit index, which can be different between the 2 fruit that appear in a single level. Since 32 is not evenly divisible by 7, this means some fruits are more likely to appear than others. The fruits with lower IDs, and therefore lower point values, the cherry, strawberry, orange, and pretzel, have a 5 out of 32, or about a 16% chance of appearing. The higher scoring fruits, the apple, pear, and banana, only have a 4 out of 32 chance of showing up. This means that the expected point value of each fruit that appears, starting on level 8, is just over 1,234 points. Now, the fruits that appear in the maze don't stay in one spot like they do in Pac-Man. They move around the maze as well. The last thing the game uses randomness for is to determine exactly what path the fruits will take as they roam around the maze. See, a fruit will appear from one of the sides of the maze, do a loop around the ghost house, and then disappear from another side of the maze. For each of the 4 mazes, there are 4 different entrance paths it can choose from, and then 4 different exit paths it can choose from, giving it 16 unique paths it can take. I actually want to go into detail about how the fruit paths work, since it is pretty neat, but it'll make more sense to start from the ground up and look at the code that controls it at the end. First, let's look at how the game stores the paths the fruit take. For the entrance path, there's 2 parts, the fruit's starting coordinates, and the path the fruit takes to the middle of the maze. All of the entrance paths need to end on this exact tile. This is because after the entrance path is complete, the fruit will take a hard-coded path in this exact shape around the ghost house, regardless of the current maze. Once it gets all the way around, it will switch to its exit path. The exit paths don't need any coordinate information since they all start from the same location. The path should end off-screen, however. All of the paths the fruit take don't interact with the maze at all, so they could even go through walls if they were programmed to. The paths are just a list of directions to go, tile by tile. So for example, this entry path would be described as starting at this location on the screen, then moving 4 tiles left, 3 down, 9 left, and 3 up. The hard-coded path around the ghost house is always 6 tiles left, 6 tiles up, 9 tiles right, 6 tiles down, and 2 tiles left. Then say this exit path would be 4 tiles left, 3 down, 9 left, 3 up, and 4 more left. The game stores these paths as a list of directions where each direction takes up 2 bits. 0, 0 for up, 0, 1 for right, 1, 0 for left, and 1, 1 for down. Frustratingly different than how directions are encoded elsewhere in the game. These bit pairs are stored in order, and then grouped into bytes starting from the end of the list. If there's not an exact number of bytes in this step, the remaining bits are just filled with anything to pad out the final byte. Then these bytes are stored in reverse order in the ROM. Since these paths don't have a predetermined size, the length of the path has to be denoted as well. This length is stored alongside the starting coordinates for the fruit entry paths, as well as a pointer to the path data itself. This means each path table entry includes 5 bytes, 2 bytes for the pointer to the path data itself, 1 byte for the length of the path, and then 1 byte each for the x and y coordinates of the starting position of the path. The exit path table entries are also 5 bytes since the 2 path types share the same code, but the starting coordinates are ignored since those are already known. Each of the 4 mazes have 4 entry paths and 4 exit paths, except the third maze, which only has 3 paths each. In this case, 2 of the table entries each have identical path pointers and starting coordinates, but only 3 paths are defined in the ROM. That means there's only 30 paths total in the game, so why not take a look at each of them? For the mazes that have 2 tunnels on each side of the screen, which is all of them but the third maze, there is 1 entry path and 1 exit path per screen exit. Some of the exit paths are just reversed versions of the entry paths, but some of them are also unique. There's also nothing preventing 2 fruit in the same level from using the same paths each time. For the third maze, there is only 1 distinct entry and exit path for the left side of the screen, but the right side of the screen has 2 variations like the other mazes, including 1 section of the exit path that actually grazes the ghost house going in a counterclockwise direction, which is unique to that path only. Since these entries are listed twice, they have double the chance of being chosen. The 5th and 6th mazes don't have any unique fruit paths. They are identical to the 3rd and 4th mazes' fruit paths, since the maze layouts are the same as well. Now that we know how the path data is stored, let's look at the code that is responsible for choosing one of the paths. This routine is entered in 2 separate cases, once when the fruit is entering the maze and once where it is exiting. Each entry point loads in the proper pointer into the HL register and converges to this subroutine. This first block of code picks the proper pointer from the list of pointers corresponding to the maze that is currently being played. Once we know what maze we're on, a random number is fetched from the R register again and logically ANDed with 3, which results in a number between 0 and 3. This gets multiplied by 5 in order to get the possible numbers of 0, 5, 10, or 15. This is because the entries into the path tables are 5 bytes long. The next block of code indexes into the table by this offset and copies the first 2 bytes, the pointer to the path data itself, to a particular memory address to be accessed later. Then this last bit copies the length of the path to another memory address and sets up a counter to the constant hex 1f. This counter is what is responsible for the bouncing animation the fruit does as it makes its way through the maze. At this point, the exit path code concludes, but the entry path code returns back up to the top here. Before returning for good, the next 2 bytes in the path entry table are copied to another location in memory. These are the initial position of the fruit, which is why this is only run in this case and not the other. And that's that. Despite all of these additional random elements, Miss Pac-Man is still quite a deterministic game. Since the ghosts are only random at the very start of each level, an experienced player can still wrangle the ghosts around the maze with enough patience. It's really only the fruit patterns you would need to look out for, and if you're going for a high score, you just have to hope that you're given more of the higher scoring fruit throughout the course of the game. Again, if you're interested in more in-depth dives into Pac-Man mechanics, I have a few other videos on my channel you will likely want to check out. Thank you so much for watching, and see you next time.